Hello, everybody. Good morning. My name is Felicia Kedrowski, and I worked with Dr. Ramakrishnan and my postdoc Mari to create two materials, Max and MX scenes, add them to epoxy to create an ink, and to create our final goal is to 3D print them using direct ink printing. So these two materials are incredible, and they are highly valued because of their two properties. They're one, mechanical, and two, electrical, because they are utilized in applications with extreme conditions like electromagnetic shielding in fields like aerospace and marine and engineering, where it's either they're in space or in deep sea, where they're going to be in very cold, very hot temperatures, and need to be able to maintain their structural stability. And so we ask the question, why do we need to do this in the first place? And it all comes back to epoxy resins. And epoxies are used in a huge amount of applications because they have pretty good mechanical strength, but their ability to stay strong in extreme conditions because they're flexible and can maintain their durability after stress is applied. But the issue is they're not conductive. They're very insulative. They have a very low conductive properties, and there is room to improve their mechanical strength. So we ask the question, how do we even widen these applications even further for applications like electromagnetic shielding? And that's by adding something called fillers, which are materials that we're going to be adding to epoxy in different concentrations to strengthen it and allow it to be more conductive. So, and in the study, we're going to be synthesizing from scratch both MAX and MX scenes and perform rheology, which is the study of flow. And that means we're going to see how much of a solid and how much of a liquid that these materials will be after adding MAX and MX scene to this epoxy. So to do this, we start off by creating MAX, and that's by adding the pure forms of titanium, aluminum, and carbon in the form of graphite and specific mole ratios. And we add that to a container with a steel ball in it, and we shake it up for approximately 6 hours with intermediate breaks. And that's to have a homogeneous mixture. And then we crush them into pellets that are maybe like half an inch wide and about a quarter of an inch thick and everything. And then we put it in the furnace to approximately 4,500 degrees Celsius. So we actually get that structure of max that we would like. And then we grind it back into a powder so we can add it to the epoxy. And we create maxines from max. So we create maxines by etching the aluminum layer away from max. And to add it to the epoxy, once we have it back grinded down into that powder, we added max in concentrations of 20, 40, 50, and 70 weight percentage. And we added maxines into 40 and 60% in order to compare these two properties. So for our research, our results, I'm going to take you to that first graph on the left. We're going to be looking at the uncured. So this is before this goes into the direct ink printing, and we're seeing the mechanical properties. We're going to be looking at the first behaviors, and this is going to be telling, and all we need to focus on is the storage, the relationship between the storage and loss modulus. And all we need to know is when the storage modulus is higher than the loss modulus, our material is going to act more like a solid. And when the loss modulus is higher than the storage modulus, our material is going to be much more liquid-like. And as we can see in the graph, that as soon as we get above 50 weight percentage for both max and MXU, this is going to be more of a solid. And this is what we want for direct ink printing. Because after our material is extruded, we don't want a puddle. We want it to actually maintain its form before it's cured. So if we were going to 3D print it, we're going to be looking at weight percentage of higher than 50%, 50 weight percent. And then on the right of that time sweep, this is going to be measuring our recovery. And we just run the same test again and see if it models the same behaviors as it did the first time. And then we can see that for the 40 weight percentage, we do see a high amount of variation, but that very top yellow line, that 60 weight percent of MXU, we see amazing recovery. So this is a great sign to say in these extreme conditions, when stress is applied, that this can go back to its original structural form and perform the same as it did before. And next graph I'm going to take you is called the flow curve. And all we need to do is see, this is going to be measuring our flow behaviors. And what we want to see is a property called shear thinning, because after the material is extruded, we want to be able to control the shear rate, like the shear extrusion or the rate that it's extruded from. So once it's extruded, we want to see it more of a liquid-like, because pushing through a solid through an extrusion is very, very difficult, and it's a lot more easy if it's much more liquid-like. And so that means when shear is applied, we want to see a decrease in viscosity. And that 60 to 8% of MXC in that very top yellow line, we can see it starts off at a high viscosity, but after that shear rate keeps increasing, it goes to a lower viscosity. So it's becoming more liquid-like, and we do see that shear thinning behavior that we want. And then that third graph on the right is going to be our cured rheology. So this is after it's extruded and going to be tested for the electrical properties. And that dielectric constant is testing the conductivity. So the higher dielectric constant, the more conductive this is going to be. So as we add more max and more MXC, it becomes more conductive. In that 68% of MXC, we can see it has the highest conductivity. So this is going to be amazing for applications like electromagnetic shielding. So for our conclusion, we were able to successfully synthesize both MAX and MXC from its elemental components, and we were able to get these pure structures that we were able to test through rheology and also our electric testing to see the conductivity. And so our conclusion, at least for right now, where there's a lot more ways to go, but that 68% for the MXC and epoxy composite has enhanced mechanical and electrical properties compared to just epoxy on its own. And this gives us an amazing path for our future, because we can expand our testings in the different weight percentage instead of having our 20, 40, and 60. We know that we need a weight percentage of higher than 50%, so we can do intermediate testing for different weight percentage loadings for both MAX and MXC. And we can actually, we're going to be working on it in a couple of weeks now, where we are going to be able to print this material. And we're going to be looking for the 70 weight percentage of MAX and the 60 weight % of MXC, and then actually see that how that looks in a 3D printing scheme. And then we're just going to be taking that cured ink and seeing the rheological and curing properties in much more detail, because I was only able to show you 3 graphs today, but it's amazing what we can do with this ink, and there's so many ways to go. So thank you so much. This has been my presentation. It's been an amazing program. Thank you so much.